Welcome to another Saturday Morning Physics. Thanks everyone who's here in the audience, in the lecture hall, and also thank you for everyone who's tuning in at home. And thank you for your support of Saturday Morning Physics. I wanted to note that after today's presentation, there will be a question and answer session. And if you would like to ask a question, you can do so. Those here in the audience can write that down on a card, or anybody can email it to physics.umich.edu. And we'll compile those and go over them at the end. So it's my pleasure today to introduce my colleague, Professor Leopoldo Pando Zayas. Leopoldo, he is a professor of physics here at the University of Michigan and a string theorist who studies the connections of string theory including to gravity, which he'll talk about today, and to black holes. Leo grew up in Cuba, and in 1989, he was a silver medalist in the International Physics Olympiad, which allowed him to move to study at MSU, which is Moscow State University, which is what was then the USSR. He has spent time at the Institute for Advanced Studies near Princeton, at Santa Barbara, at the International Center for Theoretical Physics in Trieste, Italy, and he came to the University of Michigan in 2002. He's also made major contributions to advancing diversity, equity, and inclusion, and also to outreach. So thanks, Leo, very much for joining us today to present your talk, which is entitled A Quantum Hologram for Black Holes.
Thank you very much. Nice introduction. I want to emphasize that this is my first slide. So as you can see, I'm supported. Obviously, I'm a professor here in Michigan, but I'm also supported by the Department of Energy, which in fact is supported by you with your taxpayer money. So in a sense, this is your money getting back to you. So I want to talk today about, so this is the title, A Quantum Hologram for Black Holes. So it's going to be a long journey. I want to start from the very, very beginning of gravity, which is Newton's law. And my goal is to tell you a little bit about the exciting research that is going on now in this area. So Newton's law explains how two bodies attract each other. So there's a law, very specific law. So it's proportional to the masses of the body and inversely proportional to the distance, so how far they are from each other. There's Newton's constant, and this is sort of a picture. So the two bodies with masses M1 and M2, they attract each other with this magnitude, and the force is attractive. So this is a slide that I use in my freshman physics class. So I want to just set the stage. I want to start from something that I believe should be familiar to all of you. Newton's laws are very, very powerful. They work at large scales, and in particular, they predict the period, the time that it takes for a planet to go around the sun. And the prediction is this formula up here. So the time that it takes to go around the sun is the period, and the period is proportional to the radius or the distance to the sun to the 3/2. This is 1.5, if you think about it in numbers. And if you look at all the planets here, and even at the moons or satellites of Jupiter in this case, you will see that this is a very, very accurate description of what we see in the sky. So that essentially is sort of the beginning of gravity, the beginning of our understanding of gravitational forces in the universe. And it's very accurate. Again, this all was done many centuries ago. So here I plotted. I want to take this opportunity to introduce a few of the units that we are going to use throughout the talk. So one important unit, so this is distance, right, in the x-axis, and I'm using astronomical unit. But you can read from here that one astronomical unit is precisely the distance of the Earth from the sun. So that would be a quantity that will appear a few more times. But it's important that we know how it enters here. And then this is a year. This is the period in years. So a very accurate description of nature. This is wonderful. However, one thing that we learn as a theorist, so I'm talking from the point of view of a theorist, is that most theories in nature that we know of, they come with something like an expiration date. So they are good up to some scale, or they are good in some regime. But if you push them beyond that regime, the theory starts breaking down, and you need to come up with a better theory that will replace it and extend it. And that's essentially something that we see with Newtonian gravity. Newtonian gravity is very good at explaining, as I showed to you, the periods of planets going around the sun, etc. But for example, it doesn't tell you how gravity propagates. So it's a theory that if you have the two bodies, they are going to essentially feel the force, and that's it. So now if one body disappears, the other body needs to immediately know that the force, that the force is no longer there. That doesn't make sense in a context of, let's say, relativity, right? Because the speed of light is the maximum speed of propagation of signals. So Newton doesn't know, the theory doesn't tell you what happens exactly in this situation. And you need to fix it, and the fix, of course, is general relativity. So it's a theory that contains gravity, but it allows gravity to work in a different regime when things are moving very fast. For example, when things are propagating, there you can no longer use Newtonian gravity, you need to use general relativity. So, and just again, to set a stage, so if our sun disappears right now, for 8 minutes, we wouldn't know about it, because there's no, 8 minutes is the time that it takes light to propagate from the sun to our orbit. And so on. There are a few other numbers here that I will refer to light minutes or light year, because that's a very good quantity to use in the astronomical context. So again, the speed of light is a very large number, but it's a finite number. It's 300,000 kilometers per second. So this is, whenever you have a theory, you need to make sure that it accounts for that situation. Okay, so I want to now go to an experiment that will help for us understand what general relativity is doing. General relativity states that if I have a very heavy object, this is space-time, this is the fabric of space-time. If I put an object, it's going to bend the space-time. This is not a Newtonian picture. This is now a general relativistic picture. And then if I have a few small planets around, they will move, but they're moving in the already bent, already deformed space-time. And of course, I can study this, but I need to now use general relativistic laws. And for example, if some very heavy object happens to go around, it will drag all the planets, and it will create a particular pattern of motion. This is something that now we can use general relativity to study. All right. So this is, again, the main statement of general relativity is that space-time itself, the stage where things were happening, is actually active. It gets bent and modified by the presence of matter. But not only that, not only we gain this conceptual advantage of understanding how matter interacts, we actually are able to answer all questions. So astronomers have been observing the skies for many, many centuries, and they notice that Mercury has an orbit that is not quite elliptical, right? So in Newtonian gravity, planets must move in perfectly elliptical orbits. So they go around once, and they go back to exactly where they were, and they go around, and so on. But in general relativity, there's a correction to this motion, and the correction can explain the fact that the closest point of Mercury, this is a picture of Mercury and the sun, so the closest point of approach, this is called perihelion, from Greek, Helium is sun, and Perry is closest. So the closest approach of Mercury to the sun oscillates, so it precesses. And this number was already known. It's 43 arc seconds per century. It's a very small number, but this was explained precisely using Einstein's general relativity. And of course, this is sort of like the first application of general relativity, but there are many. And in particular, so Tim asked you to turn off your phone. Your phone they have this global positioning system, GPS. GPS is a constellation of satellites that keep time very, very accurately. And to do that, you need corrections that come from general relativity. So general relativity is now in your pocket, all right? So this is important that we know. It's a theory. It's very good. And it explains very accurately what we see. But I want to now, that theory, general relativity, predicts that there are black holes. So now I want to say a few words about black holes. So first of all, I want to make sure that we do not believe that black holes suck everything around. That's not a good property. That's not even a property of black holes. Black holes essentially behave from far away. They are like astronomical objects, and we will see that a little bit in the talk. But one thing that is true is that the black holes come with an event horizon. And it is true that once you are behind the event horizon, you cannot escape, all right? And this is a matter of principle. Again, I'm a theorist, so for me, the important things are things of principle, not technological so much, whether you can do it in principle. My question is whether it is possible. And once you're behind the horizon, it is really impossible to escape away from the black hole. And the way that you should see it is not that, well, maybe if I have a very, very powerful rocket, I can escape. It's not like that, because it is as follows. So suppose you want to go back in time, right? So that impossibility, we can move to the right, we can move to the left, but we cannot go back in time. There's an arrow of time. We always go to the future. So the space-time gets so twisted behind the horizon that your future never goes away. So your future is inside. And that's really that level of impossibility. The impossibility for me to start moving back in time and wake up, et cetera, et cetera. No, you move always forward. This same impossibility is the one that prevents you from escaping from a horizon. It's not a technological, that it takes too much energy. It's not like that. It's a matter of principle. And that is why this is a very fascinating object that we want to understand. And for a theorist, this is like a candy store. It's the perfect place to study how gravity works. I want to also emphasize, because we're talking about theories that come with expiration length, not date, but length, that gravity itself, we know, is giving us the wrong answer to the question, what happens at the very center of the black hole. In general relativity, at the very, very center of the black hole, you have infinity. You have things like the curvature of a space-time is very, very large, extremely large. And we know that that cannot be right. But so far, this is the theory that we have. Again, it's very, very good at telling your phone exactly where you are, because it's a large distance question, but it cannot answer the question of what happens at the very, very center of the black hole. So when we use these theories, we always have to be mindful that there is this situation. All right. So as I emphasized, because of all these contradictions and because as a theorist, we are looking for the right place to get some good information for our theory. This is why we study black holes, and we think that the key to answering many questions is precisely there. All right, so now let's go to what are the fingerprints of a black hole. How do we know for a fact that this situation is describing a black hole? I want to go back a few years. When I was in graduate school, as Tim was saying, the idea that black holes were real was not there, right? So it was still a question, maybe there are black holes, maybe it's just a mathematical construction. But now we have a lot of evidence, and we will go through the evidence. So this is telling us that, yes, these objects are there, and we can detect them. So the way to detect them, like the smoking gun that, yes, this is a black hole, is it goes through these simple computations. So the solar mass of if you have a black hole of solar mass, all the mass must be concentrated in a region that is smaller than 3 kilometers. So I know this is hard to imagine, so let's go to the next example. So you have to imagine that all the mass, everything that is on Earth, on planet Earth, can be compacted to 9 millimeters. And this is like a grape-size region. So imagine every single thing that is on our planet Earth contracted to a situation of where everything is in a 9 millimeter radius, right? Grape size. So this is a very, very violent environment. This is an environment where we expect that our notions of space and time are going to be challenged. And that's what we need to do. But these are black holes. These are more or less theoretical. The ones that we have observed are the black holes at the supermassive black holes at the center of galaxies. We have evidence for a black hole at the center of the Milky Way, our own galaxy. And then we have even better evidence of a black hole at the center of M87, which is a distant galaxy for us. There are other experiments that also lead to this conclusion that there's so much mass in such a small region of space that there's no other explanation than a black hole. And that we can get from LIGO that can track collisions of black holes and mergers of black hole into bigger black holes. And of course, the king or queen observation is the Event Horizon Telescope. So let's go a little bit over this evidence because it's very important, and I think it's one of the most exciting things that has happened in science recently. So here are the recipients of the Nobel Prize, Physics Nobel Prize in 2020. We have Roger Penrose and Reinhard Genzel and Andrea Ghez. So the theorists got half of the prize. This is really usually not the case. Theorists usually do not even get Nobel Prize because it's not something applicable. But in this case, Penrose was awarded half of the prize because he showed, obviously, with many other people in the 70s, this work led to the conclusion that black holes are necessarily a consequence of general relativity. If you have general relativity with very generic conditions, you will have a black hole. And Genzel and Ghez, they developed experiments that really track, they track for many years the behavior of stars close to the center of our galaxy. And again, the conclusion, the most plausible conclusion is that that must be a black hole. So let's actually go over their experiment. So I want you to focus on this star here, S2. And this is, okay, so this started in 95, in June 95. And what you can see here is the time. And this is the recording of tracking stars around the center of our galaxy. I hope that you're familiar with this video. It's very interesting. But look, so this S2 star is the one that gets closest to the center. And by looking at orbits, you can estimate what is the mass of the object in the center. And the mass in the object of the center plus how close this star S2 gets to the center leads to the conclusion that it must be a black hole. All right, so that's this experiment. The other evidence, very strong evidence that we have about the existence of black hole comes to us from the Event Horizon Telescope, which is actually an array of telescopes all over the globe. So here you can see examples. This is South Pole Telescope, then there's Chile, ALMA. So all over the globe, there are these telescopes. They are looking at the same point, and then they put their image together, and they conclude that there must be a black hole of this mass, 6.5 billion solar masses, at the center of the galaxy M87. Now, this is really the first experiment that I explained gives a lot of evidence that something so massive in such a small radius must be a black hole. But this is really the smoking gun of a black hole. This ring that you see here, it forms, you can orbit a black hole, I said. The black hole from far away behaves exactly like a star. But there's the innermost circular, stable circular orbit. So there's an orbit in which you can orbit the black hole in a way that is stable. So you stay there. And that is very, very close to the Schwarzschild radius, so the radius of the black hole. And this is what is being observed here. So this is really very, very, very close to the center of the black hole. This is a black hole whose size is about 120 astronomical units. So that for us to get an idea, remember, 1 astronomical unit is the distance from the Earth to the sun. So this black hole itself has 120 astronomical units. All right, so, but that's sort of like the evidence of that black hole exists. As I said, I'm a theorist, so I want to deal more with the theoretical understanding of black holes. So black holes are very, very effective in our understanding. So we have now 2 theories. I first explained how Newtonian gravity had to be modified to account for certain phenomena with general relativity. But we have another very powerful theory, which is quantum field theory. This is the theory of very, very small sizes, right? Atomic and subatomic. So this theory has been, quantum field theory, has been very effective. And in fact, maybe you have heard talks about the discovery of the Higgs particle. And now there's an excitement about the mass of the W boson. So all that refers, all those results are obtained using quantum field theory. This is a very solid, well-tested technique that allows us to understand subatomic level physics very effectively. So we have on the left general relativity for the large distances, and on the right we have a theory that is incredibly effective for low distances. So one way where these two theories, by the way, are not compatible with each other, so we do not have a quantum theory of gravity, and that's one of the goals of science, and in particular string theory. String theories, we believe we are very, very close to having such a theory. In fact, we believe we do, so we need to prove it, but I think we have the theory that contains gravity and contains quantum field theory all together. But for the most part, we are interested in black holes just because they land in the middle of this Venn diagram. So they are situations, or they provide a situation where you have to push general relativity to account for very small distances, and you need to confront questions of quantum field theory. And that's why they are such great laboratories for us. There's another, I wanted to mention that not only black holes are in this intersection here. For example, the Big Bang, the birth of the universe, is such a situation where you need general relativity because it's a gravitational effect, but the distances and the sizes are so small that you must use quantum field theory. But of course, my goal is not to talk about the Big Bang. My goal is to talk about black holes. But there are a number of phenomena that are precisely in this intersection. They're quite exacting. All right, so because we want to study general relativity and quantum aspects of general relativity, we need to confront Hawking's computation. So Hawking studied black holes in the 70s. And one thing that he noticed using a combination of quantum effects is that black holes are not really black. They actually radiate particles, and you might have seen some description of this process. So close to the event horizon, because the vacuum is always very active, creating particles and antiparticles, it is possible that one particle goes into the black hole and then cannot escape, but one escapes, and we can detect it at very far away from the black hole. So that process is Hawking radiation. Black holes actually emit particles, and the temperature of that radiation is given by this formula here. Okay? So I know the formula can be crowded, there are many things, but I want to focus on one thing only, that the temperature of the black hole, how hot it is inversely proportional to the mass. And this is really completely unexpected, because let's see what this implies. This implies, so remember, mass, mc squared, so mass is like energy, right? So if you add energy to the black hole, if m grows, then the temperature goes down. That's not what happened in the matter that we know. Most of the matter that we know, you add energy and it gets hotter. So black holes are specific in this context, and we will see an experiment in a second that tries to explain or give you a little bit of an idea of how can that happen. But this temperature It's very small. This is 10 to the negative 8 Kelvin. Kelvin is the absolute zero. So this is very, very close to zero. So this is a black hole. This is the temperature of a solar mass black hole, of course. So this is a very, very low temperature. And again, it is radiating, but it's radiating at such a low temperature that if you have a solar mass black hole, for it to completely evaporate, it will take 10 to the 67 years. So this is larger than the age of the universe. So essentially, you would not see this effect. You can turn it around as a theorist and say, well, maybe the assumptions that went into computing this quantity, the age, the time of evaporation, is really wrong. So you again stretch your theory. You use general relativity to compute, and maybe general relativity is giving you the wrong answer. So we are constantly in this area where we want to challenge general relativity. So we will now do this experiment where I will show you that by adding ice to water under certain conditions, you will see water boiling. That would be what you expect for a black hole. Add energy, temperature goes down, or subtract energy, temperature goes up. So I have to make a disclaimer in the name of scientific veracity. So what I'm showing to you, of course, is not going to be black hole matter. So I'm not going to subtract energy from water and make it boil. That I cannot do, unfortunately. But I want you to get the idea, right? So this experiment is not very clean, but at least it gives you idea. Under certain conditions, it is possible to extract energy and have the temperature rise. Okay, so Monica is going to help us. Essentially, we boil this water, this very hot water. So do we leave it? Or?
I would move on.
Oh, okay. I guess that the gods of physics did not allow me to make this trick because I said it's actually a trick. It's not the true phenomena, but maybe we'll do it later. But okay, so we have this situation. Oh, can I get As a theorist, I'm very happy because this would have happened to me and people would tell me, oh, because you're a theorist. So. All right. So, okay. So, but this is something that is telling us again that this is like in particular jargon. This is like having negative specific heat. Okay, for people who are a little bit more familiar. But this is a property of black hole. Again, they evaporate very slowly, but they nevertheless evaporate. This was a groundbreaking result to understand that at the classical level, in the context of general relativity, black holes really absorb material, and that's it. But once you allow quantum phenomena to take place, then it turns out that they are actually radiating, they are emitting particles. All right. So one other important property of black holes is that this situation is very challenging for us because now we have this evaporation and there's an immediate paradox. So you might have heard this is sometimes called the information loss paradox, and I will try to explain it for you. So one of the properties that Penrose helped establish and Hawking in the 70s is that a black hole is completely characterized by three quantities. Its mass, basically energy, charge, electric charge, and angular momentum. Nothing else, just three numbers. If you have a black hole and you tell me these three numbers, it's completely characterized. It's like this is your passport number, done. Okay? But now, here's a situation that is very confusing to physicists, or was very confusing. So suppose I create the black hole by throwing in all kinds of different matter. It can be a bench or a TV or a computer. It doesn't matter. But once the black hole forms, the only thing that remains is these three numbers. So we lose information about this was a chair, this was vapor, it doesn't matter. It sort of destroys all that information and gives you only these three numbers. And you can say, well, that's not a problem. I lost information, which is not allowed in quantum physics. But you can say, okay, it's not that I lost it, it's that it's behind the horizon, and I cannot access that, so no problem with physics. However, we just discussed that black hole is radiating. So it will evaporate, it will lose energy, and at some point there will be no black hole. And that's where the paradox becomes important. But where is the information? Before you could say, well, it's behind the horizon, I don't know. But if you wait long enough, the black hole will, remember, as a theorist, you're focused on matter of principle. You don't care about whether it's longer than the edge of the universe. Doesn't matter. You wait long enough, the black hole evaporates, and you are left with nothing. And you lost the information of what went into the black hole in the first place. So that's a violation of quantum mechanics, flagrant violation of quantum mechanics. So you have to decide, do black holes really violate quantum mechanics? And quantum mechanics essentially is a good law, except when you have black holes. Or you say, well, no, there must be some way in which I can gain that information. It's just that I don't know. Maybe general relativity doesn't tell me. But this is a big, big question. So this question, in particular, Hawking, for example, was in the camp that maybe black hole really destroy quantum mechanics, and quantum mechanics is good as long as you have no black holes around. But if there's a black hole, quantum mechanics is wrong. Quantum mechanics, I remind you, is the theory at the base of all our technological development. Everything that we do, computers, everything is based in quantum principles. So it's a big question, and that question lasted for 3 decades, back and forth, back and forth. Yes, it destroys. No, it doesn't destroy. No, you're not good to get it out. You don't know how to get it out, but it is coming out. And all this debate was going on for a long time until Hawking conceded that he was wrong, that information is actually coming out, and we need to figure out how to get it out. And so this was a very public concession. It was in the New York Times, in Physics World, in the American Physical Society. This was a big moment for this question. And the reason Hawking conceded has to do with the title of our talk. So Hawking conceded because of a hologram, but not this hologram, okay, not the hologram that you think, but the idea of a hologram. So what is the idea? The idea is that you have a 2-dimensional surface, right, like a screen, but it gives you 3-dimensional information. So you can reconstruct the relative position of objects using only 2-dimensional information. That's essentially the idea, but of course, the details were spelled out by this gentleman here, Juan Maldacena, from the Institute for Advanced Study, where I was a postdoc, and where I would return next year for a sabbatical. So Juan Maldacena postulated that this principle of holography has been around for a long time, but he found a way to make it precise, to make it not a generic, this might be equal, but no. This is essentially the same and equal to other. And what he is equating in this principle, the Maldacena conjecture that is called, is that if you have a space, this space is called anti-de Sitter, but I will go into details later. If you have a space, what is inside the space is gravity. So gravity is inside the space, but every single question about gravity, I can extract by looking at the boundary where the quantum theory, where the quantum fields live, right? So now this is perfect because we had this tension between gravity and particle. Particle was good for the small distances. Gravity was good for large distances. But now we have this equivalence, and we can try to use it for our advantage. We had all this series of complicated questions about black holes. Is information being destroyed? Is it coming out? Now I can try to reformulate that question as a question of particles, as a question of quantum particles. So that's really the big discovery that has changed the landscape of gravitation for us. Now, I want to give you another example. So this picture here is from the Large Hadron Collider, again, where the Higgs was discovered, etc. And there you have one question. If I smash at very, very high energy, 2 protons, what comes out, right? This is a very difficult question in quantum field theory, very, very difficult. And there are many ways to phrase the question, but the question is intrinsically very hard because the particles are interacting in a very strong way. So it's not enough for you to know what one particle is doing. You need to know how it is correlated with another, and it becomes an almost impossible problem. But now, in some situations, I can use the dual, basically the equivalent of this problem, as a gravitational problem. And it could be that in gravity, it's a very easy problem to solve. It might be the problem of a planet going around the sun. And that can give you information about something very complicated in the particle world. So I know it can be mind-blowing, but it works, right? And it gives you some answer. And the kind of hologram that I want to use this is the picture of the talk. So this is from an article that I wrote for the Viewpoint Journal of the American Physical Societies. So they asked me to summarize these developments for the larger community of physicists. And the picture that they helped me construct is precisely this one. So I have the black hole inside the object in gravity, and I can decode what are all the microstate, all the little contributions that make up the entropy of the black hole from the boundary theory. All right? So that's why this talk is called a hologram, because I'm using the surface, a 2-dimensional, if you wish, to get information about what is going on inside. But more precisely, I'm using quantum field theory to answer a deep, complicated question about gravity. All right? So that's really what when you leave this talk, this is what you should remember, that there's technology in string theory now that allows you to turn a very complicated gravity question into a question of quantum field theories that you can solve. And then you can check. So that's what I'm going to tell you for the rest of the talk. Now, what should we look for, right? So this is the entropy of a black hole. So all the formulas this is the full formula. So I'm going to, of course, in a public talk, I don't want to write too many formulas, but this is one that is so pretty that it needs to be here, and I will explain. So A here is the area of the horizon. So it tells you that, and we will discuss what entropy really means, but for now, let's say this is an important property, quantum property of the black hole. So it's the area of the horizon. You have a sphere, it would be the sphere around which is the sphere that determined by the event horizon, and again, I explained, if you go behind, you would not be able to come out. So that area determines the entropy of the system. All right? But then you have G. G is Newton. I show you in the first slide. So my freshman physics students know G, and so should you. Then there's H bar. H bar is a constant. It's Planck constant, and it's a constant for quantum. Whenever you see H bar, some quantum physics is going on there. All right? And so then we have the speed of light here, c. It's relativistic. And we also have Kb is the Boltzmann constant. So this is the one that has to do with thermodynamics. So black holes, and this formula in particular, should convince you that it's a confluence of a lot of interesting areas in physics. There's quantum aspects, there are relativistic aspects, there's gravity, and there's thermodynamics. And that's why we want to study this quantity in particular. And moreover, what we want to do is to explain it using the hologram. So I want to construct a hologram that will, when I compute its entropy, will give me precisely a formula like this. That's our goal. So again, for a sense of measure, I have been always quoting aspects of a solar mass black hole. A solar mass black hole, I show you in one of the slides, has 3 kilometers radius. So the entropy is a very large number, 10 to the 77. So a 10 with 77 zeros. It's a very large number that we would like to understand. All right, so black holes have temperature, they have entropy. So that's what the general relativity has established. But now, as a quantum physicist, I immediately question what is going on behind that description. And what I mean is this. So when we have a gas, or we have some system, we usually know that, yes, I can describe it by saying, oh, my tire has this pressure, or there's this volume. So I can use some number like this, macroscopic. But I know that what is really happening, the pressure is the result of molecular motion that hits the wall of your vessel, and that's really what creates, that's microscopic description, is the one that leads you to macroscopic quantities like pressure, etc. So what we would like to construct or to understand is the entropy that we know the black hole has such entropy, very large. And the question that we want to answer is, what are the molecules? What is the microscopic? What is the fundamental description of that entropy? So in a sense, I'm looking for what are the molecules whose motion accounts for that entropy of black hole. So I want to now try to understand the temperature and the entropy of a black hole from a microscopic, more fundamental point of view. All right? So that's what I want to do, and essentially what I have done, what I have been doing in my research for the last 4 or 5 years. And of course, I want to give you some flavor of what that entails, right? So because of that, I want to propose some counting problems. I will, of course, I will convince you that these are the kind of counting problems, more complicated ones, but these are the kind of counting problems that lead to the answer that we're seeking. So the first question that I have, and this is a serious question, so I want you to try to answer it before I give you the answer. Suppose you have $10. You want to form, so the question is, how many ways you can form $10 using bills that are 1, 5, and 10? So I give you 30 seconds to figure it out. Anybody? 4. Oh, I see 4. This is a good, audience. So I need to recruit some of you to do graduate work with me. So 4, right? Because I can have 10 ones, 5 ones, and 1 5, and 2 5s. These are the ways. So now I can, and this is usually what happens in science. So this one we can figure it out just directly we count. I can go with a slightly more complicated with 20. So if you're really good at math, you will think about using this method of just splitting, and you will come up with the answer 9. But in fact, what we do in science is to find a more powerful way to answer any question of this type. And the more powerful way comes with this function. It's called generating function. So if I expand this function, the coefficients will tell me the answer to all those questions. So if you want to answer how many configurations your atoms can get organized to form a solid, I will have to set up my computation in this way. Of course, this is the idea, and it's important. The idea is the same. You just count. But the methods of counting get slightly different, more sophisticated or less sophisticated. But that's the idea. Now, why are we interested in counting? We are interested in counting because, and we will do an experiment in a minute, but we are interested in counting because we want to understand, we have so many molecules around with different possibilities, different motion. So we need to understand, we need to quantify how many ways you can form a configuration, a given configuration. And entropy enters in our discussion because the entropy, or maximizing entropy, determines what is the most probable or most likely configuration. That's why we are interested in these counting problems. And just to be precise, in a situation where my energy is fixed, it's called microcanonical for those who care. So if I fix the total energy, the entropy as a microscopic quantity is given by the number of ways, this omega here stands for number of ways in which I can arrange my microstate, my molecules, to give me a total energy E. So that's why counting problems are at the heart of what I'm doing, because I'm interested in obtaining the entropy that Hawking obtained as a macroscopic quantity, like the pressure of your tire. I want to explain that using the molecules of counting molecules. That's what I need to be very good at counting. So now we move to this experiment, which I hope will not blow up. And this experiment is something, in fact, I had the picture. This picture is from the Henry Ford Museum. So if you go to the Henry Ford Museum, you can play, well, you can see this game being played. There are many, many lessons that come out of this game, but the idea, I have many, many marbles here, all right? And I'm going to drop them in the middle. There are many nails, right, in this board. And when a marble hits a nail, it has equal probability to go left or right. That's really what matters. And what happens is that when you do this exercise, all right. So when you do this exercise, this is a funny distribution. I knew it. But okay, so there's very little probability for a marble to, There's very little probability for a marble to go all the way here, but nevertheless, we had some interesting marbles that decided to do it. But in statistical physics, we want to answer questions about this kind of situation, probabilistic. So I can ask, if I have n marbles, questions like this, how many marbles do I need to throw on average such that, I get 3 here? And you will see that there's some number that must be very large. Most of the marbles, what they want is they want to stay around the center because they have equal probability to go left or right. So they go a little bit to the left and a little bit to the right. And on average, they end up in the center. So what you have seen here is more like this Gaussian figure here, that this is the Henry Ford. So my experiment was a failure, but you go to Henry Ford and you will see the actual experiment working. Now, let me emphasize one thing that is very important. So you might say, well, you just, there are nails, boards, these are big things. There's nothing quantum. Why is this related to quantum at all? And the reason is the mathematics is the same. So obviously the physics is very different, but the possibility of going to the left or to the right, I can think about it. I have a system of a spinning particles. They can have a spin up or a spin down. If they can have it with equal probability, the question of how many particles I need what is the probability of all of them to spontaneously have spin up is the same probability, the number as a counting, is the same counting that I need to say, how is the probability of a marble going all the way here to the left? So mathematically, and I am obviously a theoretical physics, mathematically it's the same question. Of course, the context is slightly different. This was a classical experiment, and it had a priori nothing to do with quantum, but the mathematics is the same. That's why I proposed that experiment. All right? So now, let's go back to our black hole. We had this statistical mechanics diatribe, so now let's go to the black hole. So my problem in the black hole would be this. I want to use Boltzmann formula, the formula that tells me your entropy really comes from counting all the ways that you can have a black hole with a given mass, charge, and angular momentum. Given your molecules, you have to determine what are your underlying degrees of freedom, but now it is a counting problem, right? And I told you we have heavy machinery like generating functions to answer those questions. So that's what I would like to have, what I would like to do. And from the gravity now, we are going to go a little bit further. So I have been explaining that the entropy is area divided by 4, and that is true. But because if I take gravity as a quantum theory, there are usually corrections to the main term, right? So like if you, there are usually corrections. In the case of gravity, there are some corrections they are called logarithmic corrections. They are logarithm of the area divided by Newton's constant, all right? So these are very tiny. Let me give you again an order of magnitude. So we saw that for a solar mass black hole, this number was 10 to the 77. So in a 10 with 77 zeros, I'm going to now talk about a term that is going to be just 77, order of 100. So it's a very, very tiny correction to the big entropy, but this correction is a quantum effect. So it's come from particles that are created and annihilated from the vacuum. It's a very specific quantum property of gravity. And what I can do is essentially, as I said, beta has really a quantum nature. It's about particles that appear and disappear from the vacuum. And my goal is to compute this using first the hologram, the quantum field, where I can do my counting of particles, right? More or less the same way that we count marbles there. And I want to do it directly in gravity. And if these two approaches match, they tell me your hologram is really working, and it's working at this very high precision level. Those are the kind of computations that I have been doing. All right. So, of course, I think I have shown you already too many details, but I want to just go back to jump to the result. So this is something that we did with my former student Vimal and Wen Li. Wen Li was an undergrad at the time. Now he's graduating from Princeton University, and my colleague Jim Liu. So this paper appeared in Physical Review Letters, and it's a one-loop test of quantum black holes in anti-de Sitter space. So I have been avoiding anti-de Sitter, but anti-de Sitter, these are toy black holes. They are theoretically interesting and manageable, but they don't live in our space. Our space is Minkowski, so these are different spaces. They are curved spaces. But nevertheless, we managed to do the computation that I described at the beginning. So we know from gravity that little tiny logarithmic correction, the 77 in the exponent, and we were able to do that directly using the hologram, the quantum field theory, and using gravity, and we found agreement. So my technical slide is going to be this one, so that you see. So basically what we did was to use numerically we computed the form of the entropy, and a lot of simulations went into this, but if you look at these numbers here, minus 0.4999, 4996. So for the theories, these are all minus 1/2, right? So we obtained this directly from the hologram, and this quantity, this minus 1. So n, and now we have understanding of what we're doing. So the black hole is described by n particles in the hologram. So now the subleading contribution to the entropy come with this number of particles, but this coefficient, the beta, is minus 1/2. So we did that, and again, it was a big success for our field. And but again, there was some, as a theorist, using a lot of numerical simulation was not a great thing. So we wanted to prop this in a slightly more analytical way, and that is work that I did with another set of collaborators, Nak-Woo Kim and Dong-Min Gan from Korea, and Francesco Benini from ICDP in Trieste, where I also spent time as a faculty associate there. And we did the computation. Now, this computation, I wanted to present it a little bit, it's sort of towards the end of the talk, to show you what is in the toolbox of a theoretical physicist, string theorist working on this. So, of course, you need to be good with computers and do simulations. But for this particular computation, we use, so this is a knot, a figure 8 knot. And the answer for our correction, instead of minus 1/2, has all these numbers. I want to explain what G is. G is the genus of a surface. So black holes in our space, in Minkowski space, they must have a spherical horizon. The form of the horizon must be sphere. That's a theorem also from the 70s, Penrose, Hawking, etc. But in the space where I'm playing, in anti-de Sitter space, black holes actually can have, the topology of the horizon can change. The genus that I explained, that I had before, is explained here. So a sphere has genus 0. Genus 1 is a donut. Genus 2 has 2 holes. Genus 3, 3 holes. So at the topological level, genus is a topological property of a surface. Topology means that things that can continuously be deformed into another, they are equivalent at the topological level. All right? So I take a coffee mug or a coffee cup, and if it has one handle, if it has 2 handles, it doesn't work. But if it has one handle, I can continuously deform into a donut. So topologically, they are the same, and they have genus 1. So what we did in the previous work was to consider certain spaces where you construct them using topology and other properties more mathematical, but essentially that's the kind of tools that are required to do these more advanced computations. So with that, I'm getting to the outlook of my talk. So essentially, what's next? So hopefully I convince you that, that as a community, the string theory community, we have a good understanding of precision counting for black holes that live in anti-de Sitter space. So that's a big success. But of course, that is always how science works. So you were able to explain something and you say, okay, what is next? What is the next? The next step for us will be to try to answer dynamical questions. So answer questions like, the black hole is evaporating. Can you tell me exactly how is the information leaving the black hole in the radiation that you capture? So that's the outstanding question of our field right now, being able to use the hologram to answer that question precisely. So after, of course, we use the hologram to answer the quantum question very precisely, we have hope that we can go on and answer those questions as well. So, and again, I want to emphasize, this is for us the main question of our field. How is the information actually escaping the black hole radiation at the level of a form? So with that, I want to thank Marina and Max. Marina is my graduate student, and Max is a beginning graduate student. They helped me with the slides, and then my wife, Elena, corrected many of my mistakes in this talk. So thank you very much.
Thank you. Thank you very much, Leo, for that wonderful lecture. And extremely interesting topic. So before we actually go to questions, and if you have questions in the audience, please, Karen will be going around to collect the cards if you have them. And also, those of you at home or even here in the audience can email questions still to physics@umich.edu. So I thought Monica should have another chance with this demo to start the question and answer period. Describe what you're doing.
All right, so first I am boiling the water inside of the container, and then I'm going to seal it, and by boiling the water, it displaces the air and has water vapor in there. And then when I seal it and flip it upside down, I'm going to place ice on top of the container, and the problem I had was I didn't seal it enough, and so the pressure was a bit high. But once I put the ice on top of the beaker, it will reduce the pressure inside of the beaker, and then you will see that when you lower the pressure, it actually allows water to boil at less than the 100 degrees Celsius.
So don't listen to this explanation. The real thing is that this is black hole matter. So it's
Okay, great. I guess there was a lot of pressure on you to get that going. So. All right, so we have a lot of questions, it seems. So let me start with people back to trying to understand black holes a little bit better. And here's a question that said, I've heard that black holes are black because the escape velocity at the event horizon is the speed of light.
yes. So that is very accurate. However, this is one way to think about it. When I teach general relativity, I also have one class that is discussing this issue, because if you think about it only in terms of escape velocity, you would be wrong, because escape velocity is the velocity to escape just with having that velocity and then enough to escape. But you can have a comet or a rocket that will be with propulsion that can get you out. So that does not explain the real reason why you cannot explain. The real reason is that the space is turned in a way that your future is never outside. So your future is inside the black hole. So it's really a changing in the space-time. The escape velocity is a good analogy, but as many analogies, it's good, like this black hole matter boiling, right? So it's not really precise, but it's a good idea to understand roughly what's going on. But when you go into details, this analogy fails. The main reason is really the structure of space-time behind the horizon of a black hole.
Great. Okay. A couple of questions about the black hole at the center of the galaxy. How did it form? And how do stars form, et cetera, everything else with that black hole there?
All right. So this is a little bit outside my area of expertise. So I roughly, so gravity is attractive, and so most of the gravitationally bounded objects in the universe, they form because gravity is attracting. So you start accreting matter, and that process can go on for a while and create these black holes at the center of galaxies. And so stars are formed at a different stage, and they can be orbiting those black holes. But again, I don't really know the nitty-gritty details of black hole formation in the center of galaxies and star formation. That's for astronomers. I'm a lowly theorist.
Okay, well, here's another toughie. Is there a mass at which black holes become unstable?
Okay, that's a good question. Unstable to
sense.
what? So black holes in a stellar evolution, they are like the end. So you can have a neutron star, or you can have. So you can form different stars depending on the initial mass from which you start. So it can be dwarf star supported by electron degeneracy, or neutron star supported by neutron degeneracy. But black hole is sort of like there's nothing beyond that. In that sense, that's it. But if people had in mind some other instability, I'm happy to hear. But
So they're intrinsically stable, according to...
They are stable in this sense.
General relativity.
Yeah.
Cool. Is there a limit to how small a black hole can be?
Very good question. There's no limit. In fact, there are some searches in the phenomenology community because it is. I mentioned a solar mass black hole will evaporate in a long time, longer than the age of the universe. But a very tiny black hole might be evaporating now, and there's a search for this kind of primordial black hole that can be very, very tiny. So again, they have not been detected, but theoretically and for many reasons, we believe that those objects might be around. In fact, there was at some point discussion whether they might contribute to black matter, etc. Dark matter.
I see. Dark matter could be black holes, or little black holes. Great. It's a couple of questions about observations. One is, in these images that you showed from the Event Horizon collaboration, I think it was, what made the light?
Very, very good question. So I mentioned the innermost stable orbit. So it's an orbit in which you can have light orbiting. But also, because there are other matter around, the matter is accreting into the black hole and it is radiating. So those are the two main components that you see from that ring. Again, accretion of matter that is going very fast into the black hole and emitting radiation, and light is also allowed to orbit at that radius.
So maybe related, has Hawking radiation in fact been observed, or some indirect evidence of this?
No observation of Hawking radiation.
So there are antiparticles or partners to whatever gets captured coming off. Is there symmetry of matter and antimatter that would be radiated by a black hole?
I'm not sure. I'm not sure if no, because in principle, so the Hawking computation for radiation applies to a scalar field to almost any field. It's something that it sort of does not distinguish between matter and antimatter in any particular way.
So this is actually my question, just a little bit. So conservation laws like this, matter, antimatter, I think, or maybe more specific conservation laws like, sorry to use a very technical term, but flavor.
Yes.
Or something
yes.
like that. So those are all very much quantum mechanical.
Yes.
And of course, Hawking radiation is also quantum mechanical. So would these laws apply?
Very good question. So the statement, the clean statement that I can make is, in a true quantum gravitational theory, there are no global symmetries. Right? So all this obviously they can be violated for a black hole, but in the true theory, these are not good symmetries.
So all the things that we observe in our laboratories on Earth, like the LHC, et cetera,
Right.
The black hole is not that kind of laboratory.
Right.
Okay, so I'm gonna read this. I'm not sure I understand the question, but let's see if we can parse it. So in the last slide, there's a mention of M-branes. Is there any symmetry knowledge or application for black hole information related to brains, I guess, is the...
Okay, I don't see membrane, but
I think the second last slide.
That's your question.
Okay. Yes. So, sorry. Yes. So yes. So the molecules, the degrees of freedom that we use in the hologram to describe the black hole. So the second kinds of black hole that I described, they were obtained using these degrees of freedom of a M5 brane. So this was a technical title. I just took it directly from the article. I wanted to show the article, but yes, these membranes, they are actually 6-dimensional objects. And since people ask, I'm happy to oblige. So these are 6-dimensional objects, and then you wrap them in a 3-dimensional space, this hyperbolic space that is obtained by taking a 3-sphere and extracting from the 3-sphere a knot. That's what I had the knot picture there. So it's a very interesting part of mathematics. This is called dense surgery in topology. So if you do that operation, you will end up with a space on which you can wrap your membrane, and that is the best description of the corresponding black hole. So for that, I can do my counting, and I know, because I know topology, I have those tools, and that's why membrane appeared in that. So membrane is on the particle side of the hologram, not on the gravity side.
Interesting question about when black holes collide. So the phenomenon that we think has produced the observation or observed gravity waves by LIGO and others. Is the mass of the combination less than the sum of the two black holes? So they merge into a single black hole, presumably. And is all the mass of the single black hole equal to the mass of the progenitors?
Right. So I will answer a slightly different question. I will answer a slightly, but more accurate, right? So more accurate. So entropy, one of the things that I was discussing was the black hole have entropy. The entropy is proportional to the area. And now when two black holes collide and form one black hole, they merge into one black hole, the area of the resulting black hole has to be bigger than the area of the progenitors, right? So that's the cleanest statement. The area must grow, must be the area of the resulting black hole is bigger than the area of the two. Now you can relate the area if your black holes are simple. If they are rotating, the formula is a little bit more complicated. But I sort of convinced you, or at least I mentioned, that the size of the black hole is spherical and is proportional to the mass. So area is proportional to r squared. The radius is proportional to the mass. So the area is proportional to m squared. What must happen is that the resulting m is greater than m1 squared plus m2 squared. So that's your guiding principle for black hole merger.
Cool. Here's a question about the astronomy of the stars orbiting black holes. Given the gravitational redshift, we actually had a few questions mentioning that, or time dilation, is this observable in the stars near black holes? Maybe you showed a simulation, but there actually been observations consistent with that.
Okay, I would say this. I would do the same thing. I will change the question a little bit. So I also showed the picture of the Event Horizon Telescope, and there you saw a ring, but one part of the ring was very bright, and the other part was a little bit more opaque. And this is essentially like Doppler effect type of thing, or redshift, if you wish. So things are rotating, they are moving very fast. So things moving towards us have a slightly different frequency or we receive a different frequency from things moving. There, in that picture, in that situation, you can really see this shift of frequency. In the center of our galaxy, I'm not so sure that you can detect that as a big effect.
It's an astonishing thing, this black hole at the center of the galaxy. We have some questions maybe to maybe explain a little bit more about how string theory turns into quantum gravity. What is it about string theory that has gravity in it?
Right, so string theory is a theory of a string. So instead of trying to quantize a point particle, you try to quantize string. And once you embark in that journey, many things happen. In particular, you have the dimensionality of a space-time has to be 10, etc. But one of the things that is an immediate consequence of trying to quantize that object is that you have a spin 2 particle in that theory, and that would be the graviton. That would be an intrinsic quantum description of gravity. So that is immediately in string theory 101. You immediately get the graviton on the second class of a string theory course. And then you can study the implications of having that particle in this new theory. And now this is let's say the canonical way in which gravity appears in a string theory. We can also the way that I describe it here for you using the hologram feels a little different. But in fact, the origin, the reason why there must be an equivalence between a theory with gravity inside of some space and a theory without gravity at its boundary comes also from a string theory, from quantizing certain objects in a string theory.
Is big G somehow a feature of string theory?
Sorry?
Big G, so the gravitational constant.
Gravitational constant is an immediate consequence of a string theory, yes.
Wow, amazing.
In 10 dimensions, then you have to reduce it to the Newton that we observe, but in 10 dimensions, it's there.
Okay. The question about topology and that wonderful video that you had of a donut changing into a coffee cup, changing into a donut. Is the volume preserved when this topological transformation happens?
No, volume is not preserved, distances are not preserved. This is not this is not the kind of question that topology asks. It doesn't ask questions about distances, it asks very generic questions about shapes
Okay. The shape of an object. And then I think there's a very general question which we'll come to at the end, but a rather specific one about holograms, so an understanding of sort of holograms of light, and whether this is in fact somehow related to interference, which is a feature of holograms of light that allow two to go to 3 dimensions, or is this just a projection, or maybe projection isn't the right word, isn't this just 2 dimensions, information from 3 dimensions being encoded onto 2 dimensions? I say just, but of course it's not simple.
Do you want to answer? Because maybe it's more your purview than mine.
No, actually I don't. I just wanted to really know why you call it a hologram.
So I call it hologram not in a deep meaning, but in the more, not me, but the whole community calls it just because what I have been explaining. So there's a theory that, let's say, is a 3-dimensional theory with very complicated dynamics, and I can reconstruct every single process by just knowing what the degrees of freedom on the outside are doing in the surface. And that's, it's the whole idea of a hologram as a postcard for Christmas or something where it's 2-dimensional, it's 2-dimensional, but it gives you this sense because you have information about the phase of light in that case that gives you this sense of depth. But there's nothing deep about we calling the holographic principle. That's just that.
Cool. And this is maybe a sort of broader question in physics, but when you talked about the expiration date
Yes.
or the sort of scale at which a theory breaks down.
Yes.
Is there actually a real boundary where this happens, or is it just that we have systems of such different scale that we observe that we actually don't see a transition from one regime to the other?
So generally, let's take quantum mechanics. Quantum mechanics is a good example. So generally, there's some scale, rough scales at which you need the new theory. Like, for example, to explain the hydrogen atom and the different levels, this is something that it's very difficult. Well, it's impossible to do using Newtonian mechanics. So usually there's a scale. Now, technology is now advanced in a way that you can create systems in which these things are very complicated and you can see quantum effects at a large scale. But the rule of thumb would be like, at this scale, this theory stops working and you have to come up with a new, better description. But again, I want to make sure that there are many experiments and many situations, especially in condensed matter, where you can engineer systems that will not behave as unexplaining, but the idea in general is that there's a scale below which you need to change your description.
I think that applying that question to the general relativity versus Newtonian mechanics, I find the perihelion advance of Mercury really quite amazing, really quite surprising that this is a scale that we sort of almost can think about, right? The scale of the solar system, at least we've learned to think about that. I know that, for example, when we have school groups come in the summer and study the length scales in the solar system, they make a model of the solar system that extends across the diag to sort of try to give you at least a sense of the ratios. So this is almost our scale, right, to understand this. And it's there. General relativity is there. Yeah. Really quite amazing. Okay, well, that's it for the questions we have. I think they were really interesting. And thanks very much for the questions from the audience and the questions that came online. And thank you so much, Leo, for a great lecture and discussion.